Hi, welcome back to the class. I'm Ishwin Desai, your physics tutor, and today here I am with the very next chapter, that is the electrostatic potential and capacitance. Well, students, these are the topics that we will be covering here in this particular chapter, and in this today's session we will be sticking with three of the subtopics. That is, the number one, we will be looking at the electrostatic potential energy. The number two, I will be introducing the term electrostatic potential, and then finally we will be also finding out a potential due to a point charge, and of course some questions that will help us in understanding the concept in much better way. Now students, to start with this, the very first thing, the word potential energy, right? So if you remember in your grade 11th in the chapter 6 and 8, the term potential energy has already been introduced to you guys, right? Now what does it state? What does it tells you, right? Let us say whenever you're having some external force, doing some work on a body in moving from one point to some another point against the conservative forces, right? Like for example, here in this case I have taken a gravitational force, which is the conservative force, we can say, right? So what is happening here? There's an external force is doing a work in lifting this box from a one point to a some point by a height h. So there is a work done by this external force, right? So whenever you do a work against the conservative forces, that will be getting stored in the form of potential energy. Now at this height h, the box is having some potential energy, right? If I remove the external force from here, you will see that the box will fall down, thereby carrying some kinetic energy. So when it gains kinetic energy, there is an equal amount of loss in the potential energy, right? So the overall energy will be always conserved. Like this was one of the example. Like for example, you can also consider a spring force. Now what about the electrostatic forces, or else in the very first chapter we have learned the Coulomb's law, right? For two stationary charges, the forces between the two charges is directly proportional to the product of their charges and inversely proportional to the square of the distance of separation between the two, right? Now this electrostatic forces, or else a Coulomb's law, this is also a conservative force. Now if you just see, it's not that surprising guys, if you just see the gravitational force right here, the universal law of gravitation and the Coulomb's law, right? So both these equations are square of the distance of separation between the two. Like for example, in the case of universal law of gravitation, the distance of separation that we are saying for the center to center mass distance, and here in this case of charges, it's the distance of separation. Now the only difference that you will find here is in their proportionality constant. Now here, now students, if we just see if we can define a potential energy for a masses in a gravitational field, so why not for the charges, right? So here we can also define an electrostatic potential energy for the charges in an electrostatic field, and that is what we will be learning next. Well, now let us consider capital Q to be my source charge, and let us imagine a small q to be my test charge, which is placed at point R. Now what we will be doing here is that we will be moving this test charge against the repulsive force due to this source charge. Well, now before we do this, before we look into this picture, right, let me make some assumption. The very first assumption that we make here is that the test charge that we are considering to be of very small in quantity, so that it does not disturb my source charge. The second assumption that we make here, the force that we will be applying on this test charge in moving, right, will be enough to counterbalance the electric force due to this source charge. Now what happens here is that, yes, the net force that is acting on this test charge would be a zero. That means the charge won't be accelerating, or else I can say that the charge will be moved with a very small constant speed. That is what I can say when I say external force applied here is enough to counterbalance the electric force. Now the assumptions are done. Now let us see here. We are applying some external force in moving this test charge from point R to a point P. Now what we are doing here, right? So if you just see, the work done by the external force is positive. Why positive? Because the direction of the force, external force, is towards this side. Even the displacement of the test charge is happening in the same direction. So the work done by the external force is positive, right? Or else I can say here the work done by the external force is against the electric force due to this source charge. Well, now our test charge is at now point Q, the point P, right? Well, now what I do here, I just take out the external force from here. What will happen? There will be a electric force, there will be, or else I can say that there will be a repulsive electric force on this my test charge, and that will make this test charge move away from my source charge. So what has happened here? When the charge was at that point P, it had some potential energy, right? And that potential energy will be getting converted into a kinetic energy. That makes, that will make the charge go in this direction. Well, now if you just see, the overall energy, that is the sum of kinetic energy and potential energy, is still conserved, right? So basically here we are talking about the conservative forces. Our electrostatic forces are also a conservative forces, right? Well, now what I can say here is that if I want to write this in a mathematical form, I can say that the work done on this charge Q and moving from a point R to a point P, I can write it as the integral of R to P, product of external force into a dr, right? So what is that dr? The small change in displacement that we are making when we are taking this test charge from point R to a point P, right? Now we know that the electric force is exactly opposite to the external force that we are applying here, right? So the same equation I can rewrite it as minus integral of R to P electric force dot dr, right? Now why that negative sign is coming? We know that here the electric force is towards in this direction, whereas the displacement of the charge is exactly happening in opposite direction, and that is why the negative sign comes, right? Now for every point in the electric field, the particle with the charge Q will be carrying some electrostatic potential energy, and the amount of energy that will be nothing but a difference between the potential but at the 2 points, that is potential at a point P here and potential at point R, right? Well, now if you just see this equation, the right hand side of the equation clearly tells you that the work done depends upon the initial and the final position. So I can say that the work done by the electrostatic field in moving the charge Q from one point to the another point, right, it is independent of the path that it has taken. So again, we are talking about the electrostatic forces, so which are conservative forces, right? The second point that you can see here, the electrostatic potential difference has some physical significance with the quantity work done, right? Whereas when you see a potential energy, there's no physical significance. So what it means is that even if I add some alpha constant to this term, right, something like this, right, so that alpha will get cancelled out, and adding up this alpha constant, right, has not affected my potential difference. So that gives me a freedom in choosing my potential electrostatic potential energy to be at 0. And what I do here, I will be considering my electrostatic potential energy to be 0 at infinity, and when I do that, this is what I can write it. So while defining a potential energy of a particular charge Q in the presence of electric field of any arbitrary charge configuration, I can say that it's the amount of work that has to be done by an external force in bringing a charge Q from infinity to that particular point. This is how I can define. Now students, we define the electric potential energy of a charge Q in terms of the work done in moving that charge Q in that electrostatic field, right? Well, now students, if you just see here, the work that has been done here is proportional to the charge Q. Since at any point here in this electrostatic field, the force that is exerting on my test charge is a product of charge q into an electric field, and here the electric field is due to my source charge, right? Well, now students, if I say here, right, the work that we are doing in moving this test charge, right, will somewhat give me the characteristics of the electric field, right, which are associated with this source charge here in this case, right? Well, now students, this leads to the new idea about the electric potential, which says the work done in moving the unit positive charge from one point to another point against the electrostatic forces, that will be my electric potential difference. Well, and if I want to write this mathematically, this is how I can write it. If you just see here, the electric potential difference between this point P and R has got some physical significances here, because if you just see here that I can relate it with the work that has been done in moving the charge from one point to the another, right? But here in this case, students, if I consider electric potential only at a point P, or else electric potential at the point R, there's no physical significance, right? So that allows me, students, in choosing the infinity to be my as a reference point, and at a infinity the electric potential will be 0. So considering the infinity as my reference point, I can define the electric potential at a particular point in an electrostatic field, right? Now students, the electric potential in an electric field at a particular point, I can define to be as the amount of work done in moving that unit positive charge from infinity to the particular point against the electrostatic forces. Well, now students, the SI unit of measuring the electric potential is the 1 volt. So I'll say, students, when you do a 1 joule of work in moving that 1 coulomb of charge from infinity to this particular point, that will give me a 1 volt electric potential at this point P. Now students, here we are having a source charge capital Q, which is placed at origin O, and let us say we are interested in finding out an electric potential at a point P, and let that point P be at a distance of R from my source charge. Well, now students, we know that if you want to find an electric potential at any point in an electrostatic field, we must calculate the work done in bringing a unit positive test charge from infinity to that particular point, right? And the work done here is independent of the path, since we are talking about conservative forces. Well, here the path that I will be considering will be along the radial direction from my infinity to the point P. Well, now students, let us consider a test charge Q0 to be placed at some arbitrary point P dash, and let that point P dash be at a distance of R dash from a source charge. Well, now students, I know that there will be an electric repulsive force exerting on my test charge due to this source charge, and that will be pointing in this direction, right? So what I do here, this direction I will be considering as a positive, so anything opposite of that would be a negative, right? Now we are interested in moving this test charge against the electrostatic force, right, or as the electric repulsive force. So if I want to move this test charge by small displacement, let us say of delta R, from this point P dash to some point A, right, I have to apply some force on moving it, right? And the force that I'm going to apply should be equal and opposite of electric repulsive force, so that the charge is not accelerating here in this case, right? Well, now first of all, students, if we just see the force that is exerted on this test charge, right, by Coulomb's law, I can say that it will be a 1/4 pi epsilon naught product of the two charges, that is a source charge capital Q, and here in this case is my test charge Q0, and this test charge I have considered to be as a unit positive charge, so it will be of 1 coulomb, right? So that will be a product of two charges capital Q into 1 or divided by the distance of separation between these two charges, that is R dash square, that would be my force. Well, now as I said, students, the force that I will be applying on this test charge in moving against the electric force, right, will be exactly equal and opposite, right? So the external force will be, I have to just put a minus sign for the force that I have got it using the Coulomb's law. Now the work that is done here, right, a small amount of work has been done, so that will be a dW is equal to product of force into a displacement, that is let us say a small displacement of dr dash that is being done here, right? Now if I use this first equation, right, and this equation, so what this equation will look like, the dw will be equal to minus 1 upon 4 pi epsilon naught capital Q upon r dash square dot dr dash, right? Yes, so this is the equation that we have got. Now if you just think, students, here, right, you will wonder that, you know, this is the negative, you know, that you are getting here, right? So what I have done, students, I have considered the direction of the force to be as negative, since it's equal and opposite, so that is fine. Now the dr that I have chosen here, a small, you know, change in displacement, I have not taken the minus here. I know that we are doing the displacement, you know, exactly opposite to the direction of the electric repulsive force, right? But I have just kept it as it is because that will be taken care of, you know, when we will be doing integrations from, you know, limit infinity to this point of r. So that time it will be taken care of. So students, anyways, if you just see, if I just say that dr dash is negative, and the negative that will give me a work done by external force to be as positive, and that result we will be getting, of course. So let it be at this particular point, okay? Well, now what we have to do, right, as I told you, if we want to find an electric potential at a point P, we have to find a work done on a unit, bringing that unit positive test charge from infinity to this point of r where we are interested in, right? I get a point, you know, P, which is at a distance of r from my source charge, and that is what exactly we will be doing now. So the capital W, the total work done, will be integral of dw, right? And the limits will be here from infinity to the point at a distance of r from my source charge, right? And that equation I can write it as integral of infinity to the r minus 1 upon 4 pi epsilon naught capital Q upon r dash square dot dr dash, right? So that's the equation will look like. Now here in this case, the capital Q upon 4 pi epsilon naught is my constant, so I can just take it out of the integral, and this equation will look like something like this, right? So you can see now we are having the integration of infinity to r 1 over r dash square dot dr dash, right? So well, now what we have to do here, I will be doing an integration part separately, and then we will be coming back and again resubstituting here in this equation. Now this is the integration that we are having here, and to solve this integration I'll be using the general power formula of integration, which is this formula. Now before I use this formula, students, I'll be just doing a very small step, that is I'll be just taking the r dash square from a denominator to the numerator, and this is how the integration will look like, right? Now it's very simple to compare this integration with my general formula. So I can very well say that the power here, that is the n, I can say that if you compare it with integration, it is nothing but my minus 2, right? So using this general formula, I can write this integration as r dash to the power minus 2 plus 1 divided by minus 2 plus 1 limits infinity to r. Yes. Now if you just see here in the power, it's a minus 2 plus 1, that will give me minus 1, and in a numerator denominator also it will be a minus 1, right? So this I can rewrite it as minus r dash to the power minus 1 infinity to r, right? So if you just see, this is minus r dash to the power minus 1, which I can again rewrite it as minus 1 upon r dash, yes, and limits infinity to r. Now the things are very simple. I have to substitute my limits, that is the upper limit and the lower limit, into this variable, right? So when I substitute my limits, this is what I will be getting. First you have to substitute at the place of r dash, you're going to substitute the r, okay? It's a upper limit minus lower limit, that is what we're going to do here. And after doing that, you can see that only we will be having the minus 1 over r, right? Because that will, will be very negligible, coming to 0, 1 over infinity, right? And this is what we are having the solution of it, answer for the integration that we had, right? Well, now let us go back and let us substitute it in the previous equation where we had left it. Well, now students, here we had this equation, right? And we were interested in doing the integration of 1 over r dash square dr dash, right? So we have already got an answer for that, so I'll just replace it by minus 1 over r. So when I do that, minus into minus, that will become a positive, and this is what we will be having the equation, right? And according to the definition, I can say this is the potential at a point R from my the source charge. Students, now the electric potential that we have got is positive since the source charge is positive, right? Now let us say if we consider a negative source charge instead of this positive source charge, what will be the case? Now here in this case, students, the electrostatic force that will be exerting on my unit positive charge would be attractive. So if I move this test charge from infinity to this particular point, yes, in that case the electrostatic force will be in this direction, and the displacement of this unit positive charge will be also happening in the same direction. So the work done by the electrostatic force here in this case will be positive. So the electric potential that will be involved here at this point P will be negative, and that is what we will be having. Well, now students, here if you just see a graph of electric field and electric potential, okay, how it varies with the R, and here the R is a distance from any arbitrary charge configuration to a particular point in that electrostatic field, and this is how the graph will look like. The electric field, if you just see, is inversely proportional to the square of the distance, and the electric potential is inversely proportional to the the distance. So this is how the graph will look like for an electric potential and the electric field. Now students, if you just see this question here, we are having a two-part. The A part says calculate a potential at a point P due to a charge of 4 into 10 to the power minus 7 coulomb located 9 centimeter away, right? So it's again a very easy question. If you just see, we are having some charge, okay, and we have to find out an electric potential at a distance of 9 centimeter away from that source charge. Well, now students, to get an answer for this, just now here in this today's session, we have got an equation for an electric potential due to a point charge, right? So well, let me just first of all, students, write down the given thing here from the question. So I can say, students, the given here is the charge that we know here in this question is capital Q is 4 into 10 to the power minus 7 coulomb, right? The distance at which we are interested in finding out an electric potential, we know that R is 9 centimeter, which we have to convert into meter. So I can just divide 9 centimeter by 100. So that will give me 9 into 10 to the power minus 2 meter. Now what about 1 upon 4 pi epsilon naught, right? Now if you remember, students, in your first the chapter, right, this is nothing but your electrostatic force constant, right? K is equal to 1 upon 4 pi epsilon naught, which where epsilon naught, students, is nothing but your permittivity of free space, right? And it has got some fixed constant value, which is 8.85 into 10 to the power minus 12 farads per meter. So what is this permittivity of free space tells you? It tells you basically the ability of an electric field to pass through a classical vacuum, right? Well, when you substitute this value here, we know that the electric force constant is 9 into 10 to the power 9 Newton meter square per coulomb square. So this is the thing that we know, that's constant value. Well, now let us try to get the answer for this. Straight away you can substitute here 1 upon 4 pi epsilon naught. I know it's the 9 into 10 to the power 9 Newton meter square per coulomb square. The charge available here is 4 into 10 to the power minus 7 coulomb divided by, I can say here, the distance, I know it is 9 into 10 to the power minus 2 meter. Now, well, now here, students, the things are very simpler. I can just cancel out the things here. 9 and 9 will get cancelled. 10 to the power minus 2 will get cancelled with the minus 7. So here we will be left with minus 5. And once again, students, I can just rewrite this as equal to 4 into 10 to the power 9 and 10 to the power minus 5. That will become here in this case 10 to the power 4 volts. So that is going to be an electric potential at a distance of 9 centimeter from my charge of 4 into 10 to the power minus 7. All right, well, now students, let us go for the next question that we are having, by part B of it. Hence, obtain the work done in bringing a charge of 2 into 10 to the power minus 9 coulomb from infinity to the point P, and does the answer depends on the path along which the charge is brought, right? So to get an answer for this, students, straight away we know that work done is nothing but a product of charge into an electric potential at that particular point. So the charge Q, we know that W charge is already known to us, that is small charge Q, 2 into 10 to the power minus 9 coulomb. This is the charge that we are getting it from infinity within that electrostatic field. And the electric, the potential we know at that point is this value, that is 4 into 10 to the power 4 volts. So when I do that, 2 4s are 8 into 10 to the power minus 5 joules. So this much is the work done in bringing that, the small charge Q, at that particular point. So let me just show you here. Here in this case, students, exactly if you just see, we are having a one source charge, capital Q, which is of 4 into 10 to the power minus 7 coulomb. We are having a small test charge, which is placed at a point, let us say at infinity, a small test charge, which is placed at infinity. And the charge available here in this case is 2 into 10 to the power minus 9 coulomb, right? So when you try to bring that small charge from infinity at a particular point here, let us say, right, which is at a distance of 9 centimeter, right? So at this point P, we have got an electric potential here in this case is 4 into 10 to the power 4 volts. That is what we have got. And the work done here in this case is this much. That's the work required. Well, now if you just see, does the answer depends on the path along which the charge is brought? Yes. Is it dependent, guys? No. We are talking about conservative forces here. Electrostatic force is a conservative force. And since it does not depend upon the path, right? It is independent of the path, right? The work done here is independent of the path that it has taken. Now, students, if you just see this question here, the figure 1 shows the field lines of a positive point charge, and the figure 2 here shows the field line of a negative point charge, right? And altogether here we are having 5 questions for which we need an answer. Well, now let us solve this part by part. The very first question that we are having here, it tells us to give the sign of the electric potential difference between the point P and a Q, and again here the electric potential difference between the point B and an A. Well, now if you just see, students, here in this today's class, right, we have we know the electric potential due to a point source charge, right, which is that equation of V is equal to capital Q upon 4 pi epsilon naught R, right? So this is the equation that we have got it, electric potential due to a point charge, right? Now, what is this R, students? R is a particular distance, right, from my source charge, to a particular point, right, where we are interested in finding out an electric potential. Well, now here, let us go with the very first part of it, the figure 1. If you just see, here, students, we are having a source charge is positive. So when you're having a source charge is positive, that is greater than 0, my electric potential here, if my source charge is positive, electric potential will be also positive. So I can very well say here that electric potential is inversely proportional to the distance. Now it's again a very, very simple one, students. Here, if you just see, the point P is at a lesser distance, right, compared to the point Q from my source charge, right? So lesser the the R here, I can see more the electric potential, right? So in the case at a point of P, right, we will be having a high potential, and at a point Q, we will be having a lower potential. So I know here my Vp is greater than Vq. So the difference between them, that is Vp minus Vq, right? The electric potential difference between the point P and Q will be some positive value, right? Because the electric potential at a point P is greater than electric potential at a point Q. Well, now that's the first part here. Well, now let us go for the next second part of the question. Now here we are having a source charge is negative. So the source charge is negative. So if the source charge is negative here, right, my electric potential will be also negative, right? So here, if you just see the relation, electric potential this time is inversely proportional to the negative of the R, right? Now here in this case, the point A is at a lesser distance compared to the point B from my source charge, right? Now here, if R is less, I'll be getting a more negative value, and that will be at a point A. So the point A here in this case will be at a lower potential, right? And point B will be, I can say, it will be a lesser negative, right? So it will be at a higher potential, I can say. So here in this case, my electric potential at a point B is greater than the electric potential, at a A. So when I take a, electric potential differences between the point B and A, that will be again positive. This is what, I'm having. Well, that's the answer for this particular question. Now let us go for the second part, second question. Here, if you just see students here in this question, right, we have to give the sign of the potential energy difference of a small negative charge between the points Q and P and A and B. Again, there are two parts for this. So what has been asked here, right? We have to find out a potential energy difference between the point Q and point P. That's the first part of it. And the second part here, we have to find out a potential energy difference between a point A and a point B, right? Now here, one thing to note, we have to consider a negative charge, over here in this case, right? Now, if you remember students so far, while defining the electric potential or else, the potential energy, right? We consider a unit positive test charge, right? Yes, but here in this case, students, we have to take a negative charge and get an answer for this. Well, let us do it part by part. The very first question here, if you just see students, the first part that I'm interested here in, potential energy difference between a point Q and a point P. Well, now, as I told you students, we have to consider a negative charge. So here I'm having a source charge is positive. So let me consider a negative charge placed in that electrostatic field and let it be at a point Q, P. All right. Well, now if you just see students here, what will happen? There will be an electric, attractive force on my test charge due to the source charge, and that will be happening here in this direction. Right? Now, if I want to move it from point P to the Q, right, I have to do some work, right? So there comes the external force. So I'm going to apply some external force against this, electrostatic force, right, in moving it from point P to the Q. So work done by my external force will be a positive, right? So whenever you do a work against a conservative force, that will be getting stored in the form of potential energy. So more the work you do here in this case, right? So more the potential, I can say. Yes. So at the point P, I will be having a more potential energy, right? So at a point Q, I will be having the UQ, okay, will be a more. I can write here, it will be a more, and the potential energy at a point P is going to be a less. At a P, it is going to be a less, right? So of course, students, we have been asked to get a potential energy difference between the point Q and P. So if UQ is more, of course, the value that we'll be getting here in this case will be a positive. Well, this is the one way, and I'll just show you guys, how you can also get it mathematically also. Well, let us quickly see that, students. If you just see, students, when we define an electric potential at a particular point, we said that it's the work done, right? Electric potential at a particular point, it's the work done in moving the unit positive test charge from infinity to that particular point, right? So this is how we define an electric potential. Well, now if I just rearrange this equations, right, I can write that here in this case, work done will be a product of charge, that's the test charge that we consider, and the electric potential at that particular point, right? Well, now since whenever you do a work in moving a positive charge, right, from infinity to that particular point, right, so there will be a potential energy. So the same equation thus, right, I can replace W by a potential energy. So what I'm going to have a relation here is this potential energy will be a product of Q into V, right? So this is what I'm going to have. Now this is the equation that I will be using here, getting an answer for this particular part. Well, let us do that. Let us do that here in this case. The very first thing, students, I do, the potential energy at a point Q will be equal to, this time, students, we are having a negative charge, right? So this equation that I gave you, considering the unit positive charge, right? But this time it's negative charge, it will be a negative Q, and electric potential at a point Q, right? And if you know, students, the electric potential, we know that electric potential in our case VQ, right? Or else, I'll just write, students, here in this case, I'll just write it as the electric potential. Let me write it here as the electric potential is equal to a source charge, divided by 4 pi epsilon naught into r. So well, now students, here we are having a source charge is positive, right? And this 1 upon this 4 pi epsilon naught is nothing but electrostatic force constant, which is k. So that will be a k q by r. So this is what I'm having here in this case, right? So that's the electric potential I'm having. Now I will be using this condition. I'll be using this condition here in writing it down. So you just see here what I do here. I'll just write it as minus q, since my source charge is positive. So that will become k capital Q by, let us say the q is at a distance of r2, some distance r2 from my source charge that I have done. Same way, you can find out an electric potential energy at a point P. That will be a minus q B electric potential at a point P. That will be a minus q k q upon, let P be a point at a distance of r1 from my source charge. Now from here on, it's a very simple, students. You can just straight away calculate here in this case. Let me do that, the calculation part here. So when I take the potential energy difference between a point Q and a point P, I will be having minus K Q capital Q upon a R2 minus of minus, that will be Q K, yeah, let me write it here in the same order, right? So here in this case, students, we will be having minus K Q capital Q upon, here in this case we have taken a R1, right? So that's the R1 here. Well, now this is fine, students, right? So now I can just open it up, minus K Q capital Q upon R2, minus into minus is positive, K Q capital Q upon R1, right? So that's done. Now I can take out a common out from here. So let me take a common out. K is a constant, charge Q capital Q, these are the common thing that I've taken out. And I can rewrite it as a 1 upon R1 minus 1 upon R2. That's it. Yes. Now here, if you just see, students, right, we know that our R1, right, R1 is a distance between the point P from the source charge. So the R1 that we are having here in this case is less than the R2, right? If that is the case, here 1 by R1, R1 being a less in number, so this term that I will be getting will be a bigger compared to the second term here in this case, right? So a bigger quantity minus a small quantity, yes, that will always give me some positive value. So the work done, the potential energy difference, right, between the point Q and P will be a positive. And that's the answer for this question that has been answered. So that's the first part of this question. Now let us go for the second part of it. Now the second part is also very simpler, students. This time we having again the same thing that we have to consider. So this time again a negative charge, and we are interested in potential energy at between a energy difference between a point A and a point B. So let me just place a charge, minus Q at a point B. Let me just place it at here. Source charge is negative, test charge is negative. So there will be an repulsive force on my test charge. So if I want to, do some work, right? Yes, in moving it, right, in from point B to A, I have to apply some external force on this. So again, if you just see, students, displacement is happening from B to A, right? And the students here in this case, the force is also happening applied here in the same direction. So the work done by the external force is positive. So it's against the electrostatic force that the work is happening here in this case. And once again, it will be getting stored in the form of potential energy, right? Well, now if you just see here, UA will be having a more potential energy compared to the at a B, right? UB will be having a less potential energy, right? So again, if you take the differences, it has to be coming positive. But once again, students, let us do it mathematically as well, right? So this time, students, if you just see the potential that we're going to take here, that is V is equal to negative Q over 4 pi epsilon naught into R. Right? So that's the potential we are having, negative potential, because the source charge is negative. So that is done. Now, as it is the same way, students, the potential at a point, potential energy at a point A will be a negative is the test charge, and the potential at a point A, right? So let me just write it here. For this, V is equal to minus K Q upon R, right? So I'll be just using it here, multiply by minus K capital Q, and let A be at a distance of R1 from my source charge. So this will be R1, right? And that will be minus into minus, that will be a positive K Q, capital Q upon R1, right? Now, the potential energy at a point B will be minus Q, again, once again, minus K, Q upon this time, the distance of separation, right? From a point B to the source charge is R2. So here again, it is K, Q, capital Q upon R2. Now, it's very simple, students. We are interested in finding out a potential energy difference, right? Between point A and B. So that will be, I can take here K, Q, capital Q upon R1 minus K, Q, capital Q upon R2. And that will be again taking common out K, Q, capital Q, and 1 upon R1 minus 1 upon R2. Right? Now, if you just see, students, here in this case, right? What are we having, right? If you just see R1 here in this case is once again, less than R2. So if the R1 is less, right, which is in a denominator here in this case, so this term we will be having a bigger value compared to the second term here, right? So again, once again, that will be giving me a positive potential, right? Well, that's the answer for this one. Let us go for the next question that we are having here. Now here the question C says, give the sign of the work done by the field in moving a small positive charge from Q to P. This is very simpler one, students. If you just see, we have to find out and work done by an electrostatic force. So let me write here, E stands for the electrostatic force. That should be equal to the product of force into a displacement. Yes, and the force that we'll be considering here will be an electrostatic. Here we have to consider this time a small positive charge, and we are moving it from point Q to a B. So let us say the source charge is positive, and here I'm having a test charge is also a small test charge Q placed at point Q. And when we're going to move this test charge from Q to P, right? So this is how the displacement is happening. Displacement is happening here in this direction. Let us say S is a displacement, right? Now, both are here in this case a positive charges. So there will be an electric repulsive force on my test charge, right? So I am applying some external force in moving this test charge from point Q to P, right? So work done by the external force is positive here in this case, right? But the work done by the electrostatic force is negative, since the direction of the electrostatic force and the displacement, they are opposite. So that's the negative here, the work done. All right, so that was a very simpler one. Let's go for the next question. The next question here says, give the sign of the work done by the external agency this time, okay, in moving a small negative charge from B to A. So we are having a negative charge placed at the point B, right? And we are going to move it from B to A. So this is how the displacement will be. Now, if you just see, students, the source charge is negative, test charge is negative. So there is a electric repulsive force on my test charge. And I'm moving it from B to A. So I'm going to apply some external force in moving this from B to A. Displacement is also happening from B to A. So the work done by my external agency, or as an external force, will be product of external force into a displacement. Let us say S is a displacement here in this case, and that will be a positive, since both are in the same direction. All right, fine. Let us go for the last question that we are having. Is kinetic energy of a small negative charge increases or decreases in going from B to A? Now, of course, students, if you're having a negative test charge at point B, we know that there is a repulsive force on this test charge. And when we try to move this test charge against this repulsive force, right, we have to do some work. We're going to do some work, right? We're going to apply some external force, right, in moving it from B to A. And since we are, we have to, overcome this electrostatic force here in this case, right? So there will be a decrease in the kinetic. So kinetic energy here in this case decreases. All right. Yes, as you move it from point B to the point A, because there is at the same time there is an electric repulsive force exerting on my. Well, now students, that's the answer for this particular